Hello everyone, this talk is on the paper SubRank, Subgraph Embeddings via Subgraph Proximity Measure. My name is Wana Balalo and this is joint work with Sagar Goyal. Subgraphs are very important structures. For example, they can represent a cascade in an information network or a community in a social graph. Current techniques that compute subgraph embeddings might be supervised techniques, so they need training data, or they might only tackle with a specific type of subgraph. In this work, we present an approach for computing in an unsupervised fashion embeddings for any type of subgraphs. More precisely, the problem that we want to solve is given a directed graph G and a set of k subgraph of G, compute the embeddings of this subgraph. Our solution is to compute subgraph embeddings such that the embeddings preserve an input similarity distribution between the subgraphs. More precisely, our contributions are in defining a novel subgraph to subgraph proximity measure, in introducing a framework that learns comprehensive subgraph embeddings, and finally, in validating our approach on several data mining tasks. I will start with our subgraph proximity measure. The intuition that we had in creating this proximity measure was that important nodes in a subgraph SC should be close to important nodes in a subgraph SG. Let me give you an example. Suppose that Emmanuel wants to send macarons to Halima from France to Singapore. Fortunately, Emmanuel lives in Paris, which is the most important city in France. Halima lives in Singapore, which coincidentally is the only city in Singapore. Because of this, the macarons need to take a flight between Paris and Singapore. So, the distance between Emmanuel and Halima is given by the length of the flight between Paris and Singapore. Now suppose Emmanuel lived in Amiens and not in Paris. He could, however, get very fast to Paris, as Paris is a transportation hub in France. So we see again that the important distance is the one between Paris and Singapore. I will express this now using random walks. In our graph G, given subgraph Si and subgraph Sj, we have Emmanuel as a random surfer in subgraph Si, Halima as a random surfer in subgraph Sg, and macaron post as a random surfer in the graph G. Again, Emmanuel decides to send macarons to Halima via macaron post. Macaron post starts from the node Vi Emmanuel is visiting with probability PageRank of Vi in subgraph Si and will reach a node Vj belonging to subgraph Sj with probability personalized PageRank from Vi to Vj in the graph G. Halima will be there to receive the message with probability PageRank of Vj in subgraph J. What we can see is that in order to measure the importance of nodes in subgraph, we use PageRank, and in order to measure the distance between two nodes belonging to different subgraphs, we use personalized PageRank. The total distance between subgraph Si and subgraph Sj is a sum of all the distance between the nodes belonging to the two subgraphs. We can also normalize this proximity. I will move now to the subgraph embedding algorithm. The intuition for our algorithm is that embeddings of subgraphs should preserve the proximity distribution between the subgraphs. This is similar to a node embedding approach. More precisely, in our algorithm, we minimize the KL divergence between the two distributions, the distribution of proximity between subgraphs and the similarity distribution between embeddings of subgraphs. Our algorithm uses noise contrastive estimation and requires sampling the subgraph proximity distribution. We show in our paper how to efficiently sample this distribution using a Monte Carlo estimation. I will now move to our validation part, that is the graph mining applications. We look into 3 real-world tasks: community detection, link prediction, and cascade growth prediction. In the first 2 tasks, we'll compute embeddings of ego networks, that is, neighborhood of a node, and we will use these embeddings to represent nodes. In the final tasks, we'll compute embeddings of cascades, which are trees in an information propagation graph. First, let us give an intuition for why you use ego networks to represent nodes. In this example, Alice and Bob are 2 computer scientists using Twitter. In the image, we can see the graph, and we have a link between Alice and Diana because Alice is following Diana. However, Diana is not following Alice. A path-based similarity between Alice and Bob will return a similarity 0 because there is no path between the 2 nodes. However, the same similarity measure will return high values between Alice and Andrew and Bob. A node embedding approach will try to find a compromise between the 2 similarities. Because of this, we believe that it is better to represent nodes as their ego networks in directed graphs. In order to validate this intuition, we look at 3 tasks: node clustering, node classification, and link prediction. Our method, SubRank, will represent each node using the embedding of its ego network. We will compare against node embedding methods and against subgraph embedding methods. The first subgraph embedding method, averse average, is a method that we introduce and that computes node embeddings as the average of the embeddings of the nodes in the ego networks. The initial node embeddings are computed using verse. Sub2vec is a subgraph embedding method that was proposed in the literature. This method will again compute node embedding using ego networks. The approach is inspired by the paragraph 2vec model. We validate our work on 5 datasets, as we can see here. The datasets have different number of communities, from 1 community to 20. In this table, we present the normalized mutual information for node clustering. The higher the value fold, the better. We can observe that our method, SubRank, performs the best for the first 2 datasets, and also it gives very good results for the last dataset, the BLP. When we consider link prediction, and more precisely accuracy, we have again that a higher number is better, and our technique, SubRank, performs the best on 4 out of 5 datasets. We now explain how our proximity measure works for cascade subgraphs. In this example, Emmanuel, after sending macarons to Halima, went on Twitter and wrote about it. His followers retweeted his tweet. The followers of his followers also retweeted the tweet. In a cascade, nodes that reshared more recently are more visible to their neighbors. In the directed trees, nodes on the same level have the same PageRank, and nodes' PageRank increases with depth. So, in a cascade subgraph, nodes are more important if they are lower in the tree. So, more precisely, given a social graph G and a set of cascades graphs, CI, two cascades have a high proximity if nodes joining later in the cascade, that is, on lower levels in the trees, are close according to their personalized PageRank in G. The intuition of defining such a proximity measure between cascades is that this proximity can inform us how cascades will evolve, for example, their growth in a period of time. In our experimental setting, we take a social graphing input and a set of cascades and a time window t. We ask what is the size of the cascades after time t. Our method SubRank computes the embeddings of the cascades, and in order to predict cascade growth, we use a multi-perceptor regressor. We compare against two end-to-end deep learning frameworks for cascade prediction, DeepCas and DeepHawks. In addition, we compare against a simple baseline in which cascade is represented by the average embedding of its node. This method is called verse average. We look at two datasets. The first one is A minor, which is a dataset on scientific citations. Here, a node represents an author, and we have an edge between two authors if the first one cited the second one. A cascade contains all the citation of a given paper. The second dataset, Sina Weibo, is a dataset on social media retweets. In here, each node is a Sina Weibo user and an edge is a retweet. A cascade corresponds to the retweets of one message. We will split both datasets in three intervals, such that for the first interval we have the global network. The second interval consists of the training cascade sets, and the third interval is the test set. Here we have the results for the two datasets. We can observe that SubRank performs very well on the first dataset, A minor, and is the second best on Sina Weibo. Thank you for your attention. Don't forget to check our paper and our code.